Alright, this problem is going to use mole fraction. So we have an apparatus consisting of a 4-liter flask containing nitrogen. Remember, that's a diatomic at 25 degrees Celsius. So I have a temperature, 803 kPa, which is a pressure, joined by a tube to a 10-liter flask. So that looks like a V2, but we really have maybe is a picture. So we're going to connect these two flasks. So this is my 4-liter flask of N2 at 25 degrees Celsius and 803 kPa. And I have argon at 25 degrees Celsius. So do you see the temperatures are the same, 47.2 kPa. So I can't use P1 V1 over T1 equals P2 V2 over T2 because these are two separate samples. So if they were the same sample, we could do that, but they're not. So this would be your stopcock. So you'd have some way to, have these sitting in some kind of container or something that holds them, and then you could turn this open and allow the two to mix. So it wants to know what is the partial pressure of each gas after mixing. So what I need to know here is how much gas, so since it's mole fraction, what's N going to be? So I have my volumes of each of these two. I should have added that. So sometimes drawing a diagram, so it's like organizing what you know. So I'm going to solve for moles of nitrogen. Okay. And I'm going to use the 803 kPa times 4.0 liters over, now I'm doing N equals PV over RT. For this R, I want to use this 8.134 joules per mole Kelvin. So kPa is really the joules to moles Kelvin, so that's considered the IUPAC one, but kPa liters per mole Kelvin, and then my temperature of 298 Kelvin. So that's my 25 plus that. So when I solve for N, I'm going to get 1.3 moles of N2. I'm going to do the same thing now for argon, my 47.2 kPa, my 10 liters, my 8.314 kPa times liters over mole Kelvin. And again, my temperature is going to be 298 K, and that's going to be 191 moles. So I need to look at what my total moles are. So my N total is going to be 0.191 moles plus pressure, or the partial, plus the 1.3, so the moles of the N2, and that is going to equal 1.5 moles total. Now, I need to know that because I really need to know total pressure in order to find partial pressure. So my total pressure is going to be my total moles, so this is nRT over V, 1.5 moles. And I'm going to keep with kPa since we did that on all the other ones. Liters kPa per mole Kelvin times 298 K. Now, I have to be careful of, they now have this total volume. So this is now open and combined. So I'm going to have a total of 4 plus 10. Or 14.0 liters. So when I solve for that pressure, that's going to be 270 kPa. So now I'm ready to do this mole fraction. So if you look up here, your partial moles over your total moles. So each gas exists its own partial pressure. So I'm going to do the mole fraction times the total pressure. So the pressure of N2 is going to be 270 kPa times my 1.3 moles of N2 over my 1.5 moles. My moles will cancel, and that'll give me 230 kPa. And then finally, my pressure of argon, partial pressure of argon, 270 kPa times the 0.191 moles over 1.5, and that's going to give you a partial pressure of 34 kPa. Now, you'll notice that this doesn't add up. This is giving me 264, so that's because of some rounding. There are only 2 sig figs. We don't have a whole lot going on with that, so because this is rounded off so much, that's why we're not quite to 270. You probably could take 230 minus 270 and also show that it's about 40 kPa, so that's another way to do that. So again, not a lot of significant digits here, so a little bit of rounding issues. And that is how you use partial pressure to, or mole fraction to find partial pressures of gases.